knows the storm is coming fast. The day will soon be here when those who are caught unprepared will be the first to fall. That much is clear.
Hello and welcome to Physical Attraction, the TEOTWAWKI specials, where we'll be examining the end of the world, one apocalypse at a time.
And survive while there's people crying, people dying everywhere around.
Hello and welcome to this TEOTWAWKI special of Physical Attraction. So here we are. The topic of today is going to be climate change. I'm going to try to be as unbiased and thorough as I possibly can, but this is an area I've read an awful lot about, as I'm sure you have. And that can quite often make explaining something more difficult, as you try to remember and include all of the salient points that need to be mentioned and explained. But I will try. So the first thing to understand is the difference between weather and climate. Weather is the local conditions, for example temperature, precipitation, humidity and so on, rain, snow, that kind of thing. The local conditions that are in your area for a small period of time, perhaps a few weeks at the most. That's your weather. Climate is the average of these conditions over a period of years or even decades. So for example, the fact that it's particularly warm today, or this week, or even this summer, is not necessarily categorical evidence that the climate has changed compared to last year. Equally, the fact that it sometimes snows, or that you can bring a snowball into the Senate floor and drop it on the ground, that doesn't mean that things are getting colder either. But climate change may have an influence on weather conditions. For example, recently, in the terrible 2017 hurricane season that has affected so many, there's been a lot of talk about this. Partly because having that many Category 5 hurricanes in a single year is very unusual, and partly because the destruction they've caused has been widespread and terrible. We don't know what causes hurricanes to form. There's no closed analytical model for this, although people have lots of ideas. It's okay in science to accept what we don't know, and in climate physics there's still a lot that we don't know. But being uncertain about potential catastrophe is not an excuse to do nothing about it. As many have pointed out, if you're driving along a cliffside in foggy weather and you don't know if there's a turn ahead or exactly where the turn is, it's still rational to apply the brakes. The second thing I'd like to do is to explain why we think the world is warming and what it's got to do with carbon emissions. To explain this, it might be helpful to go back over the radiation from our older episode, Unusually Hot, that I'll briefly explain here. Lots of factors determine how warm the surface temperature of the Earth is. The most important one, obviously, is the fact that we have a sun. Without this, the temperature would probably be much closer to minus 250 degrees Celsius, and there'd be no point having this conversation, because we would all be frozen to death. So to first order, the most important thing is the fact that there's a sun. Any object with a constant temperature is in thermal equilibrium. It's really pretty simple. As much heat flows into an object as heat that flows out again. That's thermal equilibrium. If more heat is flowing in than flowing out, the object heats up. If more heat is flowing out than flowing in, the object cools down. The Earth absorbs some radiation from the sun. It also reflects some radiation without absorbing it, and it also emits radiation of its own. Obviously, because outer space is empty, only radiation really matters in heat transfer between Earth and Sun. Conduction, convection, the other things you might have learned about at school, they require matter to transmit them. So to first order, we think about the Sun and the Earth as a system in radiative equilibrium. Luckily, physics has an amazing formula for how much energy an object should emit by radiation. It's called the Stefan-Boltzmann law, and it says that the power emitted is proportional to the temperature to the power of 4. So this is great. We can calculate how much energy the sun is emitting, we can calculate how much reaches us here on Earth, we can estimate how reflective the Earth is, and so we can figure out how much the Earth absorbs. Once we know how much radiation the Earth absorbs, which is basically the amount that shines on it minus the amount that's reflected, then we know how much heat is flowing into the Earth. So then we just say, aha, if the Earth is in thermal equilibrium, it must re-emit all of that energy. because you can't have any energy flowing into the Earth that doesn't flow back out again, or it will be at a different temperature. And so this is what happens when we talk about thermal equilibrium. If energy is flowing into an object, then it will heat up until the amount of energy that's flowing out of it balances the energy that's flowing in. And this is why things that are hot glow white hot and red hot and things like this. They're emitting radiation depending on their temperature that balances whatever's heating them. So from this we can use our fancy Stefan-Boltzmann law only in reverse. We know what power the Earth is emitting. We have to know because it's the power that keeps the Earth in equilibrium. So from that we can figure out its temperature. And if you do this, you get something like minus 20 degrees Celsius. So we should all be dead. What's going on? Obviously, a little bit more detailed physics is needed. When an object emits radiation, the temperature it has doesn't just tell you how much radiation it emits. It also tells you the frequency of the radiation. And we know this really, because when you heat up a poker, it'll start by glowing yellow, then red, then eventually white hot. That's because as the temperature increases, the frequency of the radiation that it emits is also changing. So you can think of the frequency as related to the wavelength of the radiation. So you can imagine some radiation having a very short wavelength, lots of little oscillations, or having a long wavelength like radio waves with lots of big stretched out peaks. And as we mentioned in Unusually Hot, you're emitting radiation right now, but you can't see it because it's in the infrared. Our eyes are tuned to visible light, that's why we call it visible. So the Sun's surface is at around 6,000 Kelvin, where 273 Kelvin is 0 degrees Celsius, and the units are the same, so 1 Kelvin is 1 Celsius. Our surface temperature is closer to 300 Kelvin, give or take. So clearly the Sun emits different frequency radiation than the Earth, because it's way hotter. In fact, as you'd expect, the Earth emits infrared radiation just as we do, which is why it doesn't glow when we look at it. All the sort of things that are in a similar temperature to humans and ovens and so on will emit the same infrared radiation predominantly. Then you add in an atmosphere, and now things start to get really interesting. Because as we've mentioned, matter, or to give it its technical name, stuff, can absorb and interact with radiation. But the type of radiation it can interact and absorb with depends on the matter. It depends specifically on the energy levels of the atoms in that matter. So now imagine a particular type of molecule in the atmosphere. It has a particular set of energy levels. It has photons, it has radiation that it likes to absorb and it likes to re-emit at particular wavelengths. So there are two kinds of radiation that might interact with this particle. If the particle looks upwards, it'll see shortwave radiation from outer space, the powerful, high-frequency radiation directly from the Sun. And if it looks down, it will see the long-wave radiation from the Earth. It will see the low-frequency radiation, the infrared that comes from the Earth. Such a molecule might have energy levels that are too small to interact with the shortwave radiation, so this stuff can pass more or less straight through. But the long-wave radiation from Earth, that can interact with this molecule. So what does this mean? Well, it would mean that the radiation from Earth that would usually escape to space is absorbed by the particle. Now what happens is the particle then goes into an excited state where it contains the energy from that radiation for a little while. And it then re-emits the photon and the radiation scatters off again. It's re-emitted, but crucially, at a random direction. That means that around half of it will head back towards Earth, heating up the atmosphere and the Earth. So some of the radiation that could escape to space is instead blocked. These are greenhouse gases. The greenhouse gases, because this is what we're talking about, they act like a blanket that traps heat. The warm radiation from the Sun, with high frequencies, passes straight through. But the stuff that's reflected from Earth is instead trapped. It's re-radiated by the atmosphere, and it comes back down to Earth again. Now I'm afraid that this is simply completely non-negotiable. This is happening. You can argue about what impact doubling CO2 concentrations in the atmosphere, as we're currently doing, might have. You can argue about the economics of climate change if you want to. But you cannot argue, as I've seen, particularly by one individual I won't name who, surprise surprise, works for the oil industry, that the greenhouse effect is not real. We know that this is happening, because without it the Earth would be too cold to sustain life. The Earth would be minus 20 degrees without any greenhouse effect at all. It's a real phenomenon which has been understood for well over a century, and it's crucial in determining the temperature of our planet. And even in the famous paper where it was first described, in the early 1900s, the scientist Arrhenius pointed out that human influence may conceivably affect the climate. He said, quote, "The slight percentage of carbonic acid in the atmosphere may, by the advances of industry, be changed to a noticeable degree in the course of a few centuries." Unfortunately, Arrhenius imagined that this would be an effect that we might just notice in a few centuries. Instead, carbon dioxide has increased from 280 parts per million when satellite measurements first began in the 1950s to well over 400 parts per million, and it looks set to double this century compared to pre-industrial levels. So a good deal of the projections for the climate are based on this idea that the carbon dioxide levels will double. So I've described how the greenhouse effect works, and how we actually do need some greenhouse effect to ensure our planet isn't too cold for life. But of course, disrupting this balance by emitting more CO2 will cause our planet to warm by some degree. This, I think, is obvious. We can actually quantify the effect of greenhouse gases by looking at what's called the top of atmosphere flux, which is a very famous graph that I'll include in the show notes. So NASA and so on, they stick satellites up in the atmosphere that measure the radiation that's emitted from the Earth's surface, the stuff that makes it past the layers of clouds and greenhouse gases. Then they compare it to what the Earth would emit if it wasn't obstructed by anything. And they find that a significant amount of the radiation is absorbed and scattered by the atmosphere, some of which goes back down to Earth. Now, they can measure the wavelengths of the escaping radiation, and they can show you on the graph precisely which wavelengths of radiation are being absorbed. And guess what? They correspond to exactly the wavelengths that we know are absorbed by carbon dioxide, methane, nitrous oxide, and water vapour in lab experiments that we do when we test which wavelengths are absorbed by various gases. Because we can take individual molecules of these gas and shine lasers and other lights at them, and figure out what wavelengths they like to absorb. That's not that difficult an experiment for modern science. And so we can see that there's a certain amount of heat that's being trapped by all of these different gases. So using this, we can estimate how much radiation is trapped by carbon dioxide versus water vapour versus methane and so on. So you might have heard that methane is considered a worse greenhouse gas than CO2 because it traps more heat. And you can see on the graph, which I'll post in the show notes, that methane's absorption is at a higher wave number, hence higher energies, which might start to explain why that's the case. The other side of the methane debate is that methane doesn't last that long in the atmosphere, a few years, while CO2 remains where it is for centuries. That's why we think historically that CO2 has been a bigger driver of long-term climate change. So you can tell how much energy is being taken out of the system by CO2, and how much difference more CO2 is going to make. And this is fairly easy radiative physics. So you might be wondering, if this is all there is to it, how come climate physicists can't produce exact models of the temperature, and their models can't exactly predict the temperature? So this brings us on to the third major theme to take away from these episodes. The world and the climate cannot be simply expressed. For this reason, we like to call it a climate system, or sometimes even an Earth system, to indicate the whole Earth. There are thousands upon thousands of feedback loops and so on that make things more difficult. So let me give you an example. A huge resource for people who are interested in studying the climate is paleoclimate data. So using archaeology and geology, we can work out what the temperatures and sea levels of the world were many thousands of years ago. For example, ice cores in the Arctic and Antarctic. They provide valuable pieces of information on atmospheric CO2, because when the ice froze thousands of years ago, it captured some of that CO2 inside of it. And we can model how this works today, and we can infer what the CO2 content must have been in the past. Rocks form differently underwater, so from this and similar observations, we can calculate sea levels. So we know in broad terms things like what the temperature was in the past, what the CO2 was in the past, and what the sea levels were in the past. And we've been constructing a more and more detailed picture of it for many years. Incidentally, this is one of the things I really love about science. It's a similar aspect to how we know so much about outer space and the world around us and cosmology and the beginnings. We really don't have that much information, and yet, just using our own theories and our own experiments and our own understanding, we can reconstruct what the climate of the Earth was like by digging into rocks or looking at ice cores or looking at fossils. In much the same way as we can reconstruct what's going on billions of miles away in outer space just by looking at the light that we see from there. It's pretty amazing. Long ago, perhaps earlier than 650 million years ago, many people think that the entire world's surface was covered with ice. This sometimes gets called the Snowball Earth for reasons that I'm sure you can imagine. But it's difficult for us to see how this can be the case. After all, the sun isn't changing all that much in how much light it emits. The Earth's position in its orbit does fluctuate in something called the Milankovitch cycles, but it would clearly have to be a pretty big change to cover everything in ice. Under some models of Snowball Earth, the equator, which is currently the hottest place on Earth, can get up to 40, 50, 60 degrees Celsius sometimes, were as cold as Antarctica is today, and that seems hard to imagine based on any small event. So instead, the actual mechanism doesn't involve any particular event that cools the Earth. Instead, it's a feedback loop. There is a fairly small change to the climate system initially, but this acts in such a way that it reinforces itself. Before long, you have something that runs away with itself, accelerating towards a new equilibrium. So how does this happen? Let's say that the climate system gets a particularly big kick. Maybe continental drift acts in such a way as to cool everything down. Maybe there are changes in the orbit. Maybe there's a supervolcano that dumps dust and ash into the atmosphere that cools things down. You'll remember from TEOTWAWKI 7 supervolcanoes that this can happen, and it's led to mini ice ages in the past. The natural response is that the north and south poles, which are colder anyway due to Earth's orbit, start to freeze over. And when they freeze over, you get ice. Ice reflects sunlight far better than water does, as you can tell because it's basically white, and if you've ever been fortunate enough to be somewhere really icy, then the glare can be a really big problem for you. So this means that it reflects lots of solar radiation back to space. So the idea is gradually, over many thousands of years, the ice formed. It reflected more radiation back to space. This cooled the planet down, allowing more ice to form, reflecting more radiation into space, resulting in more cooling. Eventually, most of the planet was covered in ice. Now we know this effect is important in determining the extent of the polar ice caps. Historically, it's reinforced cooling trends. And Snowball Earth is actually a pretty stable climate again. The Earth is covered in ice, which reflects back lots of solar radiation. Things stay at Antarctic temperatures nearly everywhere, and little kicks to the climate system don't do much to warm things back up. But it's also possible to emerge from a Snowball Earth scenario, and everyone who believes it must accept that this happens, given the lack of snow around today. So many people suggest that the greenhouse effect was actually responsible for rescuing the Earth from its icy snowball state of always winter and never Christmas. Billions of cyanobacteria, a primitive form of life, were trapped beneath the ice of the Snowball Earth. They fed on the organic carbon that lived under the ice for many, many years, and emitted CO2. Normally, the cyanobacteria would be part of another cycle, absorption of CO2 by rocks as they weathered. But with the Earth covered in ice and snow, there was no way for the oceans or rocks to absorb carbon again. Consequently, there was a big build-up of CO2 from these cyanobacteria, and possibly volcanoes as well, that wasn't being absorbed by the Earth. And this big build-up meant that the atmospheric concentration of CO2 shot up. The Earth heated up, a band of the ice melted, and then we get the same feedback effect in reverse. The Earth heats up, the glaciers retreat, there's less radiation being reflected into space. The climate gets hotter. The climate's more temperate for the little cyanobacteria to regenerate the atmosphere again. And this kind of process may have led eventually to what they called the Cambrian explosion of life. So we can see in this that the Earth's climate history and processes are complicated, but CO2 has always been an important factor. One of many factors, but an important factor, in determining the Earth's overall temperature. Also important, and crucial to the fact that our understanding of climate is at present so uncertain, are the presence of these feedback loops. So I've described the ice albedo one, which is thought to be very important, and you can see how it would be very important. I guess it's easy for people who aren't sold on this issue to think, so what if the polar ice cap melts? It'll kill a few polar bears or penguins, but that's a small price to pay for progress. The issue is, if you really want to look at things from a superhuman-centric point of view, is that the ice cap melting could kick the climate into an unstable regime where quick, dramatic warming takes place. And we already think that this is actually a bigger effect. It enhances the effect of CO2 that's released. So at the moment, Greenland looks poised to melt, and the Arctic looks poised to melt. The Antarctic sheet will probably be stable for a little while longer. But if things get too much worse, then Antarctica could start to melt again. At the moment it's isolated from the rest of the world by a series of interesting geographical conditions, like Drake's Passage being open and winds that circulate around the Southern Ocean and things like this. But should Antarctica melt, well then we'll have a big problem, because that will cause this huge ice albedo feedback, where a region of the Earth that used to reflect radiation will now absorb it, and we'll be in trouble. There are other feedbacks too. Warmer oceans mean that more water evaporates, and there's more water vapour in the atmosphere. And water vapour is also a greenhouse gas. In fact, in some ways, it's the most important greenhouse gas, because that is the one that predominantly means that we are not at the same temperature as we should be, minus 20 degrees Celsius, but instead at a rather more balmy 10 or 20 sometimes degrees Celsius, depending on where you are in the world. Of a great deal of interest, and with no small amount of complication for people trying to figure these things out, is the cloud feedback. So yes, clouds reflect light too. And clouds are also very important in the Earth's radiation balance. Broadly speaking, low clouds reflect more sunlight, while high clouds trap more heat. I'm simplifying the literally hundreds of research papers on this topic, but you understand. So how much will climate change affect this particular feedback? Will we get more low clouds that reflect sunlight and cool the Earth? Or will we get more high clouds that trap heat and warm it up? It's not completely clear how large this effect is, but most scientists are pretty convinced that the net effect is to further warm the climate system. So one of the ways you might see why this is a predominantly warming effect is you think, if these higher clouds are trapping heat and warming up the Earth, or when things get hotter, there's more buoyancy, clouds will start to form higher up, that kind of thing. And if clouds start forming higher up and trapping heat and warming up the Earth, then it could be what they call a positive feedback cycle. That means that as temperature increases, this feedback cycle tends to cause the temperature to increase even more. But that said, we don't entirely know. Clouds are probably the biggest uncertainty in modelling the climate that we have at the moment. And uncertainties do remain, which people are furiously working on trying to understand and quantify. But unfortunately, the pernicious nature of climate denialism is helped out by how complicated Earth's climate system is. Things are particularly complicated, but one of them is that the climate does naturally oscillate, by a smaller amount now than total human warming, roughly every decade. It cools and then it warms again. And these are in part caused by oscillations you probably heard of if you followed the debate, called El Niño and La Niña. So you can see why this is such a big problem, because it means that every couple of decades we see a pause in the observed warmings of the Earth's surface temperatures. And the reason we sometimes see these pauses is because the Earth's natural cooling cancels out the human-induced warming, and so the result is a flat line. So we just came out of one now that lasted quite a while, with 2015 and 2016 being the hottest years on record again. But this is a really, really bad problem for communicating the science. Because when we emerge from a pause in warming like this, it coincides with the natural cycles that warm up the Earth. Think about it like this. You have a straight line graph going up, and you add that to a wave graph that goes up and down. What you get is a flat line, when the natural cooling cancels the human warming, followed by a spike when the two add up again. But the spike occurs when natural processes are already warming the Earth. Most commonly cited as the culprit is El Niño. So it means that every time we see a spike in observed temperatures, climate skeptics can say, this is just El Niño being responsible. And it is in part, but so are we. And the same climate skeptics who say that El Niño is responsible for the change in temperature every time the temperature goes up, well, they have to answer for the fact that El Niño appears to be getting much, much stronger every single time it happens. Why is that happening? Well, the answer, if it is true, is climate change. The reality is that it's not getting stronger, necessarily. What we're seeing is anthropogenic climate change underlying this pattern that causes us to have some spikes and some flat lines. There's a good graph that explains this, which is called still going up the down escalator, which sort of shows you how the temperature patterns have been this escalator type graph, where you have, a strong peak followed by a flat line when La Niña is cancelling out some of the human warming, followed by a strong peak again, followed by a flat line, followed by a peak. And the thing is, what you're doing overall is increasing gradually over the decades. That's climate change. So the thing is that individual statistics for a year are not necessarily all that meaningful. For climate physics, which evolves over decades, you may have to average over 10 years or 20 years to see an observable result. So I'm not willing to bet any of my meagre fortune with you guys that it will be warmer in 2018 than 2017. That's not how climate works, as best as we can tell. But I'm willing to bet that the 2030s, on average, will be warmer than the 2010s. And I'll be willing to bet that the 2050s will be warmer than the 2030s. Strangely enough, not many people seem willing to take you up on an offer like that. Maybe it's because they know that their denialism isn't true. I think one of the things that's most scary about climate change as a threat is not actually how precisely terrible it will be. If you ask me if I'd rather wake up in a world 100 years from now where nothing is done to address climate change, or a post-apocalyptic wasteland after a nuclear war, then yes, I'd probably pick the climate change world. But what it does present is a unique set of challenges that we as humans are singularly and catastrophically bad at dealing with. The problem is incredibly scientifically complex. Communicating scientific complexity to people is very difficult. The problem takes place over many decades, even centuries. And this is a huge problem because who do we need to act? Democratically elected governments need to act. Corporations and individuals need to act. Democratically elected governments have no incentive to care about what happens beyond the next 8 years or the next 10 years. They'll be out of office. Their legacies will be secured. Corporations might expect to exist a little bit longer, but ultimately the profit motive will always come first for them. And many individuals don't particularly care about what happens after they die. Or if they do, e.g. for the sake of their children, they may not always be willing to undergo the personal sacrifices that would help us in this quest. And they may consider, why should I do this when other people aren't contributing, when other people aren't helping? They have other priorities too. And alongside this, specific aspects about the complexity of the problem make it more difficult to spread disinformation. And alongside this, specific facts about the complexity of the problem make it so easy to spread misinformation. I'll be talking about that a little bit more next week. Until then, thanks for listening to this TEOTWAWKI special of Physical Attraction, which was the first part in our series on climate change. It's obviously such a huge topic and quite difficult to talk about. That means that I will need to do several episodes on this show, but I hope you've enjoyed what we've come up with so far. And if you have any questions, comments or concerns, you can find us on Twitter, or visit us at the website at www.physicspodcast.com. The Twitter is @physicspod. Either of those places, if you have anything you want to say to us, interact with us, that kind of thing, it's all good. There's also a donations button where you can give us a little tip in the tip jar for what we've done so far. That's through PayPal. Alongside that, if you want to leave us a rating or review on iTunes, that would also be very nice. And if you don't want to do any of those things, the best thing you can do is tell other people about the show. If you're enjoying it, if you think it can be improved, let me know. If you're enjoying it, then please let other people know, because as we say on here quite a lot, if every person tells one other person at the end of each episode, then I guess 8, 10, 20, 30 episodes time there'll be billions of listeners, and at that point I'll be in a position to do some favours for those of you who are here first, if you know what I mean. Until then, stay safe.
options, there's no time for hesitations. Compile a list of tips.
Our theme music is Get Ready for the Apocalypse by Astrometrics.
To get ready